All right, so tonight's the last night of class lecture. I guess thought a reminder that everything is due by this coming Sunday at 11:59 p.m. That's when the semester ends, so all the assignments will close and lock, so please get everything to me before then. Not a whole lot of attendance this evening. There were a few things I was gonna add on the list, but the only attendance to the Zoom call, so I might just keep it really short and show one thing here that is going to be really useful for those heading into software development. The last couple of weeks, we've looked at different programming languages, trying to decide what language to take after this. As long as I'm making this, the one making the schedule for software development here at Sellersburg, I can say for certain that Python, with the 200 level courses, Python will run every summer, or sorry, not in summer. Python will be running every spring, and Java will be running every fall. So you can choose between those for the 200 level course. But in general, we looked at a number of languages, right? We did the scripting, the macro, and converting some of our stuff to PowerShell syntax. There's a discussion board about just looking at some other languages in general, maybe using Ripple ID. There's just some stuff on GitHub. And there's a lot of stuff that, a lot of languages software developers seem to know. And the thing is, they all kind of follow the same pattern. Those basic tools we use to put the logic together, that's how we feed instructions into a machine. In the high level language, depending on how far you're going, there's also the lower level languages. Machine code, machine language, that shows up sometimes. The only time we really code in machine language is a very special case of it. What's called port manipulation. It shows up in IoT devices quite a lot. And for HID, the plug and play devices, so like your Xbox controller, when you plug that into a USB port, it just automatically works for the thing you plugged into. Those are called human interface devices. And we have to write almost in machine language. It's a specific thing, it's called port manipulation. But really what that is we're taking direct control over what bits in each one of our registers are. We write code like put a 1 in register 0x87 slot 3 and put a 0 in register 29 slot 5 and take direct control at the machine level like that. Although I just kind of exaggerated that because somebody did go through on most of our microcontrollers or things that would have general purpose in out pins, like in the IoT lab, and assign names to all of those. So when we write it in the text file, we can use the name of those registers. And most of the bits in each particular register also have names. So we can use names, and then we're putting 1s and 0s in there directly. That's about the only time we work in machine language. A step up from that is assembly language, which can be a useful thing to know. And some of y'all might encounter it at some point on the way through. Those heading onto a 4-year degree after this, and most of your 4-year degrees that include programming, assembly language will be an elective. And it just so happens that Python gives us a really useful tool to access the assembly language when we write a Python script. And in general, I thought I would add that to the list of things to look at tonight, thinking it would be useful to you all for software development in general to see what the assembly language is doing, because maybe that'll help as you learn different languages. And a couple other things on the list I was going to go through, like Google searches and look for most popular and kind of fill some space. But since there's not a lot of attendance, I guess we can go ahead and wrap it up quickly. But I do want to show this Python library that can be immensely useful for understanding what's going on in the machine. I'll go ahead and start up Spider, do some quick stuff in Python, and this will go really quick. Which, yeah, if nobody else shows up, we'll just do a quick thing and then I guess call it the end of the semester. Class wasn't canceled or anything, so I'm not sure where everybody's at, but once Spider starts up, we'll take a look at this. So like we've seen many times, close that and get just the template file. Whenever we write a new script, we often import from other modules and do stuff. And I'm going to write a little function here. Nothing too fancy. Define a function. Double and loop. And it's going to take in some parameter. I'll call it X. And then I'll just double whatever is in X is X times 2. And then we'll loop through that many times for I in range from double to 0, stepping by -1. All of that stuff we've seen before, right? Working in our high level language, we use mostly keywords, we use special symbols to make things happen. And I guess in this case, I'll just print the number is going down. It's currently plus whatever the number is. As double in as a string. Oh, but not double. As I as a string. That way we can see it go down. Print then afterwards we can print and that's all. So nothing too fancy, things we've seen before. Just some function, maybe we have a reason to do all that. And then down in our guard statement, we call that function, let's say double and loop with the number 14. We pass in some number and then that's going to run. Go give this a save real quick. That name will make more sense in a moment. I'm gonna call it disassemble. And yeah, I'll go ahead and run it. There's nothing surprising on the loop here, right? We on the first run, we just walk through that loop, go down. But we're seeing that in the high level language. So what's going on closer to the machine level? Like what's the machine itself doing? And there's a library built into Python that we can use. So we can import the dis library, which is short for disassemble. And then instead of calling our function directly, I'm going to use that library, and it has a function called dis, same name as the library, so dis.dis, and then pass in our function to that. I want to use a double function, and maybe I'll run it 5 times because that might get long. Double and loop. There we go. Actually pass in the proper name for the function. So now when we run this, I'm not sure what that's not, okay. Not really sure what happened the first time. This is what I was expecting to happen. I was trying to get that error message again just so that I could see it clearly, but I cleared that error message out of the console and tried to pull it back up so that I could read it clearly, and it seems to have disappeared. It worked properly the second time. So we see at first, we passed in 5, we double that number and then count down and print out the last thing. But then afterwards is when this function gets called, and that dis is short for disassemble. So what this does is gives us the assembly language instructions that actually ran from our function. There's different reasons to do it. Computer scientists that are thoroughly studying what would lead to an improvement in the program, improvement in the efficiency of the program, which generally what people care about is time. If the program runs better, it's going to run faster, and people will worry about the time. So computer scientists do their research and experiments looking for things like that. Or the reason I included it this evening is it could be useful for learning software development to kind of get a sense of what's going on in the machine itself. So after that run, see, we got all this other stuff, and this is the assembly language instructions that made up that function. So first thing we're going to do is load some stuff in. So these first few things load, check if it's operation. This is kind of just setting up the program. So that's basically the if name equals name. Jump if false. So see that jump if false. That's how sort of a selection structure in assembly language. We have if name equals name. And all that's in the high level language, and that turned to a bunch of ones and zeros on the inside. And when we run that through our CPU, we're going to get either a true or false value. Actually, what we're going to do is we're going to take the thing stored as name, which is we load the file, so you get the name of that. Oh, there's somebody. I'll run this again. We haven't got very far into it. Just to show her. Hi, Jessica. There doesn't seem to be a lot of turnout in class this evening, so kind of shortened the list and was showing this very useful thing here. Let me clear out the console, and we just started talking about it, so I'll run it again so you can see it. So I made this little function, a rather trivial function. It just takes in some number, figures out what 2 times that number is, then loops through that many times and prints a statement. So nothing fancy there. It's just a function. But for those heading down software development pathways, or in the computer science pathways, sometimes it can be helpful to have a better understanding of what the machine's doing. And Python has this built-in library called dis, which is short for disassembler. And when we use this library, well, the module is called dis, and then there's a function inside there called dis. So we use dis.dis, and then pass our function into that. What it does is it will break it down and give us the assembly language of it. Obviously, going all the way down to machine language is going to be pretty meaningless to a human, right? We're going to ones and zeros. We ain't going to have a clue what's going on. But assembly language, which is closer to the machine than we normally work in our high-level languages, computer scientists might use that to see what's going on, try to figure out where they can get improvements in code. Or the reason I was showing it tonight is for software development. You know, heading down that pathway, it might, probably noticed that all of our languages for the last 2 weeks, we've looked at several different things, but all of them have a lot of things in common, which is that basic logic. The manner in which we feed instructions into a computer is consistent, and all the changes is the syntax. So developing an understanding of how the computer works can be very beneficial. And when we use this, well, right off the bat, our function went ahead and ran, so nothing fancy with that function. But afterwards, that dis function, which stands for disassemble, shows us the assembly language instructions that our high level language actually turned into to help us see what the machine itself is doing. And we just started talking about that before you arrived, Jessica, so I only went back like 2 lines. So load fast, loads in that's basically loading our program. We load in our program, and our program starts with this guard statement. If main equals main, so just part of the way the Python works is the file we hit the run button on where it gets renamed main. We've talked about that, that's why this works. So once the program's loaded in, we're going to grab another constant, in particular a string literal here. So that's what's going on in that second one. And then we make a comparison between them. And notice that in our high level language, we only put something if it's true. We only put what to do if it's true. But in our assembly language, we only get an instruction on what to do if it's false. So it says, make that comparison, and if it's false, jump if false. That's an important one in assembly language. That's saying if it's false, jump to line 62. So we're currently in line 31, go to 62, which is way down here. So we'll jump all the way ahead if it's over. But if it's not up to 62, go ahead and finish the setup, which goes all the way to line 20. So you'll notice once again, we load some stuff in, store some values. Pop has to do with a stack, and in certain situations, we might need to jump ahead again. I was going to go through these in order, but jump forward, and if we're in the situation where we jump forward, we need to jump forward to line 44. And then we load some stuff in. An attribute error. So we load in this pre-built error message. One of those error messages we're used to seeing in Python, or similar to the error messages we're used to seeing in Python, is actually an assembly language error message. And if we happen to have if we don't have an exact match, then we're going to jump ahead to line 42. But if we do have an exact match, we'll just keep doing this stuff. Pop top means remove all those instructions we just loaded in to give us that gave us that error. What that's doing is whenever we define the function, we don't want to run it, but in interpreted language, it reads top to bottom. It reads our instructions one at a time. So the interpreter has to read all those instructions. We don't want to run it yet, so when we define it, we kind of pretend like we're running it. We pass it through the interpreter like it's actually running those instructions, but we do it in a fake sort of way so that it doesn't send us any output. It just loads things in. And then if something went wrong, we'll take it back out of there. And notice that same thing happens again. Just checking to see if there's a runtime error and see if there's a traceback from the stuff we loaded. See if we're looking for a particular error. And if not, then we should be ready to call the function. Load in any values and do that. Okay, yeah. And then here's where it kept saying to jump ahead to. It kept saying to jump ahead to line 42 or 44, either one of them. If it said jump ahead to line 42, that was when there was an error message. So Reraise means we the error's been fixed, so now we're ready to continue. But if there's no error message, then we would jump ahead to line 44, which basically assemble corresponds to this line in our code. All right, we're ready to load this. Then we load in some sort of attribute, which is the 5. We go ahead and set up the spot for the 5 to go. Jump if false. So we're going to look at some condition and go to line 62 if it's false. That sounds an awful lot like what our while loop is doing, right? So notice, or that's not a while loop, but our for loop is doing. That's sort of what a for loop is about. And then these would be the assembly language instructions to represent what our value is doing. We load a number in, probably some whatever double currently holds. In order to do that, condition check. We see load fast, store. Well, I'm going to ignore the fast. So we load something, then we store something, load something else, and then we're ready to check to see if we're done, or if we want to continue. And notice this time our jump goes the other direction. So it says jump to line 50. So that's back up here. So we must be back at the start of that loop. Load in the values, the attributes we need. Well, we have one. Well, I guess you can kind of track some things. We have one name parameter, and then we have 3 arguments that we're dealing with, one of which has a name. So load fast, load fast, load fast, load fast. We see load fast show up 4 times. So that's our actual values. That's like the variable. And then this first load attribute would refer to the I. And the second load attribute, the double, which we need to store because we're going to do stuff with it. We're going to print it out here in a moment. So that one doesn't just get loaded, it gets stored. We load the value in, make sure there's a connection to the variable name, and then we actually store it to use it later. Then we load in our other 2 things. And once again, if we're still in a true condition, jump back to line 50, and that's what a loop looks like in assembly language. But eventually we'll be done with our loop. We need to jump ahead to line 62, which we saw that up here somewhere too, didn't we? Oh yeah. If name is equal to main, we do all that stuff. But we see on 1, 2, 3, 4, that 4th line of assembly language, if that name is not equal to main, we want to jump ahead to line 62. Which is, and when we finish looping, we go to the same place. So we load in the globals, a bunch more loading values and constants. So the constant's probably right here. Our other print statement had a concatenation and used the string with it. And then we set up a way to call that particular function. And notice there's references to where we're working at, the file we're working in. And then we remove it, because once again, we do that sort of a fake run of it. And then load one more constant, which is actually assigning all of these instructions to this keyword so we can reference the value of it. And then we return that value so that we're ready to use that in whatever comes next. So a very different order than we're used to, right? And it kind of looks like there's fewer steps. You'll notice that. With assembly language, we're closer to the machine. So there's actually a lot less stuff to do than we have in our high level language. For some reason, a lot of people expect assembly language and machine language to be bigger, but they're actually way, way smaller than our high level language because we're closer to the machine and the machine can only do so many things. But we can put them together in lots of different combinations. What's another quick function we could write? Define divide. I'll just do something like this. We'll pass in 2 parameters and reach z equals x divided by y and return z. So slightly different. I'll comment this one out so we don't see all that stuff again. And once again, we can just run that function, right? Call divide, and we'll divide 17 by 5. Nothing real fancy there. Let me clear the console. But when we run it, x equals that, and then print x. That way we can actually see what number it is. When we run it, we get a number, no surprises there. But what can be useful for you all as software developers heading forward, is the last 2 weeks showed there's a lot of different programming languages. And once again, all of our high-level programming languages, as you all kind of saw over the last couple of weeks, they work in a very similar fashion. We have essentially the same tools, variables and loops and selection structures and those core tools to build up our logic, but slightly different syntax in them. But closer to the machine, we also have the assembly language. Actually, I'll put it like this. So I'll print that number out, which is basically the same thing we just had. Oh wait, no, we don't need to print that. So instead of printing it, I'm going to use that dis module and call the dis function. So the disassemble function, and then that will show us what that looks like in assembly language. So when we run it, oh, that's right. Now that I see that error message, I do remember it's been a while since I used disassemble. We get that the first time. So first time you run it, it tracks everything that happens. So you run it once, whoops, then we'll clear this out, and when we hit run again, we should get the results. Maybe I do need to print that. Let's see if that works better. Okay. The function does have to fully end. So notice this one was a void function, it didn't do anything. But when we had a return value, we're not really finished with anything, right? We get a number back from the function, but usually if we do that, we're expected to keep doing things with that number that we got back. So it's not a finished point. So we do have to reach a finished point. So I'll just throw that in the print statement. And here we have the instructions for what that looked like. Is there anything surprising about that? Anything immediately jump off the page at you on that? From what we were looking at just a moment ago? Let me start scrolling and scrolling and scrolling and scrolling and scrolling and scrolling. And That's the thing I was trying to hint at there. If we look at our code, look at that in a high level language. Which one of those functions is shorter? The second one's shorter by a lot, right? We don't loop or anything. That first one is several lines longer, and one of those lines is loop, which when we count lines, we usually don't count the loop line. We only count the lines that happen inside of the loop. So if you're given a number and say something has a loop with 3 lines inside, or 1 line of code, then a loop with 3 lines inside of it, we would say that function is 4 lines, not 5, because we don't count the keywords for the loop. Those weren't our choice to write. We were just stuck with those keywords. But it looks like that second function is a whole lot shorter. But I've already scrolled and scrolled and scrolled, and that scroll bar is only halfway through what it takes to divide 2 numbers. So at the very least, you could use this to find some interesting little things like that. Like, wait a second. How is just one simple division divide 2 integers so much more? Well, how does that take so much more than multiplying the number? Because at least as humans, we find multiplication and division together, don't we? We kind of treat those as the same thing. Well, they are the same thing. Division is multiplied by the reciprocal, right? So, I write that on the board, write some math class on stuff on the board. As humans, we completely treat those as the same thing. Right? 17 divided by 5, division, which you've seen at least when your elementary school teacher was showing you how to work with fractions. Division means multiply by the reciprocal. So 17 divided by 5 is the same as 17 times the reciprocal, or 1 over 5. So we can, as humans, we completely treat those as the same thing. Let me turn on that previous line. I'll go ahead and print both of them out. I'm going to clear this so I can find the top one again. So when I run this and scroll way up to the top, let me show you which line it is. Oh, this is the multiplication. Oh wait, no, the next one's the multiplication. Sorry, I highlighted the wrong thing. I saw it on the screen. But see how we have the x? And that's what we're doing for x, right? X times x. So load, fast, loading, whatever stored in x, load the attribute 2, then store the result of that. That's all it takes to multiply. If we scroll down, oh, we've already passed the end of it, haven't we? Let me just comment that out. So it takes 3 lines of assembly code to multiply 2 numbers together, even when one of them is an unknown value as we get started. If we run that second one, it takes all of this to divide. So there's where we get our x. Load in some function, call another function. Here we load in that x, do something with it. Load the x, do something else with it. check things. We'll jump to line 56. If we have false, if we have true, we'll do that again. Load in an X, do some things with it, store what we have in X, jump forward to 108. Because up here we jump, so here's an if else block. If false, go to 56, which is only 10 lines ahead. Whereas if true, if it's not false, then it must be true. Then we'll do all this stuff and jump to 108. So 56 to 108 must be the false block. So if we look at that, we load in X, do something called GI code. Then we're loading X, do something called GI code. Load in X, do something called AG code. Load in X, do something called AG code. Load in X, do something called CR code. And we do CR code a couple times. And finally we're up to line 108. So here's what we could have skipped over. But division is clearly not the same thing as multiplication to a machine the way it is to a human, right? It only took 3 lines to do that multiplication. And those 3 lines were the first thing we did when we divided. And that was 100 lines ago in assembly language. But if we look at our code over here in the high level language, it looks like division, that function that just does some quick divisions, is going to be a whole lot shorter. But pulling up what the machine is actually doing, we can see that's tremendously longer. This time we're loading in X and doing something with a dictionary. Loading in X, do something with a dictionary. And eventually we get back to that store command because we finally figured out what X is. Oh, no, we didn't. We just made a temporary variable. We do some stuff, see if we have some code, what to do with it. But eventually, we'll return from our function. And then load in that global print and disassembly. Look where that scroll bar is. We're only halfway through the division. I guess the point I was trying to make there is some of these things can be surprising. I threw that in there to let you see that there's that first function was a lot longer than the second one in Python. But when we put them in assembly language, that second function is tremendously longer than the first function as far as what the machine actually does. So that is one thing to keep in mind heading into software development. The code we write is not what goes through the CPU. And the reason I wanted to show this, the reason it was on the list, is because as you all head down software development pathways, or maybe some of you all are here getting the first couple steps on a computer science pathway, or you're heading somewhere else in IT with technology, and just thought Python would be a useful thing to know where you're heading. Being able to look at the assembly language and try and develop a better understanding of what the machine is actually doing when you run your code will be very beneficial for you in the long run. You don't need to get to the point that you're just typing in assembly language yet. Any of you all heading on to a 4-year degree after this, for any of the 4-year degrees that include programming, assembly language will be an elective that you can take. And at that point, you would need to type in assembly language. But for now, I was just showing you this because it might be a useful tool to help expand your understanding of what computers are doing in general. Because if you've never looked at that assembly language thing before, this division thing probably might have surprised you a little, right? We went from what? 60 something lines to 358 lines. That's a big increase in assembly language, but our high level language got shorter. There's explanations for it, but as you look at a couple of things, maybe take some of the code you've already written, things you have split up into functions, run those functions through the disassembler. So import dis and then dis.dis and take a look at what's going on. And as you see, there's not very many assembly language instructions. There's less instructions than there is in Python. So you'll see the same thing over and over and over again. After you look at it, you might get kind of feel like you're getting an idea of what's going on. Notice they're all very straightforward words. We're loading stuff, calling functions, jump means to go to a different place. There's a lot less stuff that can happen. But look at that in a few places and see if it helps you feel like you're understanding computers a little bit better. That was one of the things I wrote on the list for tonight. There were a couple more, but it's really light attendance tonight. Actually, when class started, there was only one person here. I was like, huh, I wonder where everybody went. Usually there's more than one. But it's the end of the semester. Everybody's exhausted and ready to finish up, right? I was planning on ending early anyway. I had a long list, and I was planning, or it's not a long list, it's a short list. I had more than one thing on the list. But when there was, without a lot of people here, I'm thinking everybody's probably trying to finish up their final projects, because that's the important thing right now, get all that work in. And we're just looking at odds and ends. Now, what I thought would be important for you, the dis module and dis.dis will feed in any Python function to that, as long as it gets to a final return spot. So it does have to come to a conclusion. So if it doesn't, do it, edit here, and just like wrap that function into a print function, because a print is a void function. We get to the point where there's nothing coming back, and then feed that into that dis.dis, and you can see the assembly language, and that can help you develop a better understanding of what the machine's doing overall, which is going to make you a better programmer, because understand we're feeding instructions into a machine. So the better we can understand the machine, the better we can be at feeding instructions into that to get complicated tasks accomplished. That'd be one way to say that. So I had several things on the list, but that seemed like a good one to wrap up on. And we're only about 20 minutes earlier than I was planning on anyway, because what's important right now, we're at the end of the semester, right? What the important thing is making sure all the homework gets completed and turned in. And please make sure you get everything to me by 11:59 p.m. on Sunday evening. That's the 18th. I'll send out a reminder over the weekend. That was the date put on the schedule years ago, long before you all registered for the class. So the whole time you've been registered for the class, you've known that date. The semester ends on December 18th. And I do not accept late work after that date. A few semesters back, there was a guy that hit some hard times. He had a large family and had to look out for his kids first, and all that occupied his time. And then he forgot to withdraw from the course, and he probably should have withdrawn from the course because he had much more important things going on with his family, to the point that he forgot to withdraw until almost the end. And to avoid bending on that rule, I spent 6 hours digging through VA paperwork with the company and get everything straightened out so that he didn't get in a lot of trouble with the VA for the grade he ended up with in the course. So I do not bend on that rule. Make sure you get everything to me by Sunday, 11:59 p.m. And on Monday morning, I will wake up. First thing in the morning, I'll wake up to start grading. I wake up early in the morning, so I will probably be finished with the grading by about 7 o'clock. The semesters that I feel like moving slow that morning, I'm still usually finished with all the grading by like 7:30 in the morning, long before most IT people wake up. But otherwise, at the end of the semester, I always make it a point to keep my schedule as open as possible. So I have a class tomorrow evening. Tomorrow's a normal scheduled day for me. But after that, my schedule is pretty much open through Sunday, and I will just be sitting around waiting for questions to come my way. So if you have any questions on the homework, need help with anything, just let me know. We can hop on it. I'll just be sitting around ready to hop on the Zoom call and get things going. But it's an active subject we learn by doing, so there's a lot of stuff to do this semester. And the semester flew by, so you might have got behind on some of it. So please try to get all the homework finished. What do we have? There's 2 hours left in our scheduled block here. So that should be some time to work, right? This block on your schedule should be marked off that says learn software development. So please use our time productively. If you have any questions, send them my way. As always, till 8:50, the normal time on our schedule. I'll just be sitting here waiting for questions to come my way. We can hop on a Zoom call and address those. I'm pretty sure I'm the only person on campus right now except the janitor and the security guard. So I might take, the interstate's back open, so I might take 5 minutes to drive back to Clarksville and make a cup of coffee at home. But otherwise, I will be sitting there ready to answer questions if they come up. Please use our time productively. And I guess that wraps up our lecture time in this course. Thank you all for making this such a great course. You have a wonderful break. Try to relax some over the next couple weeks, and I hope to see you all around in the spring or anything. Does anybody have any questions before we wrap up? Okay, I assume 5 seconds is fine with me. No questions. Y'all have a great break. Try to get some relaxing in. I know it's been a very exhausting semester, so I will see you